Hello everyone, welcome back to the lecture. Last time we talked about correlation. We basically had two sets of data and we were concerned with if we changed one, would the other change proportionately? Would it be positive? In other words, if one increased, would the other increase, or negative? If one increased, the other one decreased. So we found out, we talked about calculating a correlation coefficient, R, and what it meant once we calculated it was between -1 and 1. -1 was the negative correlation part, positive was over on the plus side of 0. 0 was basically no linear correlation there. Our next step is to take that and see, well, they're related. Can we use the one to predict the other? Can I use the amount of fertilizer that I add to plants to predict the growth that they get? So that's what we're concerned about in 11.2. This is basically a regression analysis. Regression is building a model that we can use, a math model, a math formula. All of these are the same things. Okay, so the one that we're going to talk about is if there is a linear relationship there, it's called the least squares regression line, the straight line, and basically it's going to be a formula, this least squares regression line. It is the best fit, the line of best fit that between all of those points that we found there's some correlation to. Here is the formula that we can use to predict it, and we'll kind of do all of those things within this section. Okay, so I'm going to do away with me, no need for that, and we'll continue on. So what we're going to do is compute the least squared regression lines, use it to make predictions. Predictions of what? If I change X, what's my new Y? Interpret the predicted values, the slope, the Y-intercept of the least square regression lines. So we're going to predict this, the Y-intercept, and then use those in the model, and we're going to do those. We're going to kind of interpret what those mean. Okay, so we're going to return to the house size versus sales price. Remember, we did a correlation, and we kind of envisioned that I went through here, and I drew a straight line through here. Notice that there's many straight lines. You may have saw something a little different, maybe up here, maybe down here. The one that I would like to focus on is the one that minimizes the error between all of these points and that predictive line, here and here. Okay, and remember, if I had pluses and minuses and adding those residuals up, those errors, if it was just positive and negatives, they would all go to 0 no matter the size, as long as they were the same relative size, one positive, one negative, then they would all go to 0, and it wouldn't be useful. I mean, it would be kind of, each one of these may have different things. Basically, what I want to do is do a square to make them all positive and minimize these little pieces in here. Okay. So here's our scatter plots. Each has a different line superimposed. So it's clear that the line on the figure on the left fits better than the line of the figure on the right. How do we go about doing that? They say it's obvious. Here's the smallest errors between here. These are big in here. So this one is a better fit than this one. These are all over the place. This would have a less of a correlation coefficient than this. This one would be a greater value +1. So this would be relative 0.9, maybe 0.88, 0.92, something in there. This one is getting down to a negative, but with these large sizes, I would assume maybe, a bigger value. But look, these are the same between here, right? This is just same points. It is just a different picture, but this one would have larger errors if I tried to use this line to go through all of these points. Okay. So here's what we're trying to build. We're trying to build the equation of the least squares regression line. This is the model. This is the best model that we can come up with. The least squared regression lines, the line of best fit is another term for this. So I've got some set of data, the x's and the y's. With sample means x bar and y bar, we calculate those out, give me the mean of the x's, the mean of the y's, standard deviations. We use that to calculate the correlation coefficient R. The equation of the least squares regression line for predicting y from x is, here is the model that we're going to use. This turns out to be a straight line. If you guys remember from algebra, this is the power. Up here is understood 1. 1 is a linear. This is a linear equation. This is called the slope. That's called the intercept. And we're going to calculate B1, that, and we're going to calculate B0, and then we can predict what our y is going to be from our x value. Okay, we just multiply that by our B1 calculated, add B0. This is going to be good for all the x's, so we just calculate this one time. So if we go back, we've calculated R. You remember what that R looked like? It looked like something like 1 over n minus 1. The sum of the x minus x hat s sub x, y minus y hat over s sub y. Looks something like that. We did the correlation in Excel. So here we go back, we take our R value, we just multiply it times our ratio s sub y over s sub x. That gives us B1. And our B0, once we know that, we take x bar, multiply it times B1, subtract that from y bar, the average of the y's, and that gives us B0. And that builds this equation right there. Once we have these and calculated, we just take any x. So we know what x's and y is for here, right? We have to know the exact value. But what about if we wanted to know from a 2,900 square foot? We don't have any data from that, but we put 2,900 times B1 plus B0, and that'll give us a nice estimate for the price. Maybe 455 or something, 455,000. Okay? So the variable we want to predict, in this case the selling price, is called the outcome variable or the response variable, responds to our predictor. The variable we are given is called the explanatory variable or predictor value. We use the x's as the prediction to get the y. In the equation of the least squares regression line, x represents the explanatory variable, y represents the outcome variable. Okay, so we have all of those. Let's go back and add this. I'm going to go back here, keep. I want to go back to my Excel. Now remember, I called this B1 the slope, this the intercept. So I went right here, and I want to see how we can do that in Excel. And it turns out it is just like we see it, equals, see that slope, S-L-O-P-E, I click on that, the known y's, the known x's. So here, I need to put this in first, the known y's, comma, the known x's, and if we go back up here, that's our slope from this thing. Our intercept equals, this is how we calculate those, equal intercept. Known y's, known x's. There's our known y's. And then our known x's. and that's the intercept. I'm going to go here and I'm going to put an extra column in here, and I'm going to add this as my y hat. This is basically my predicted value. So if I went here and if I use that formula, this is the slope is equal to 2.5 times my x value. And if I add the intercept of 3.3, look what I get, 15.8. Now look at these things, these are right on. In fact, I generated this list of numbers from that basic equation, 2.5x plus 3.3 and generated, but the Excel, I went back and made sure there was no formula there, but Excel was able to do the least square regression calculations to give me the slope, the B1 and the B0, and then I used that as a model. Okay, I'll come back to this in a minute. Let's move forward here. So here was our calculations from before, our R value. Here's S sub x, S sub y over S sub x. If I do that calculation, here was the 29.684 S sub y, S sub x. That gives us a 0.099199796. Y-intercept, B1 times the x bar. I just calculated the B1. There's our x bar. Here's our y bar, and that gives us a B0. And now this is the model, the regression line, the least squared regression line, the line of best fit as 0.0992x. This is generally how it's given here, plus the 160.1939. So given some, so here's maybe 2,900 square feet or 2,950. I don't have a price. I could use this to predict 2,950 times 0.0992 plus 160.1939 gives me the selling price that I would want to ask for in hundreds and thousands. Okay. So we can do this also on the TI-84 Plus. Go back and turn diagnostic on from your catalog, turn that on, and then we can go through and basically do some things. We can do the least squared regression line. L1, L2, go to calculate linear regression. Okay, so you're going to let it know this is an L1, L2. It'll give you the R value. It lets you know the order of these things, A plus BX. Our A is 160.19 and our B is that 0.0991976. Okay, gives us the very same thing from there. So again, the reason you want to do this predicting is because you don't have all the data but for all the x's, right? Something in here I want to predict that I don't have the value. If I had some value, I can actually use this, right? But once I do this, you know, I can kind of stick, I can actually predict out here where there is no x's. I have to be careful. This is called extrapolation. And extrapolation the prices may go up tremendously or down. They may fail to continue following that linear in there. But if we wanted to predict the size of the 2800, I'd say 2800 times 0.0992 plus the 160.1939. That would be in there with the 2800, $438,000. Okay, again, here's just another predicting. This is the y hat is the predicted value. Y and x are the actual value that you're going to use. The actual value in this case, I want to calculate 3,000, but I'm predicting. I'm not using the y value corresponding to a 3000. I may not have it. I don't think I have it in this set. So I just multiply this. I use this should be the 0.992x. There should be the x there. Doing the 3000, that gives me $457,800. The y-intercept, B0, is the point where the line generally crosses the y-axis. This has a practical interpretation only when the data contain both positive and negative values of x. In our case, I would say that for the 0, that would represent 0 square foot of the house. So we don't have a structure, but we still have a price. What is that price from? That would be from the land value. You would consider the lot value, the land value, but you haven't built yet, and then you're starting to add it. So surrounding land areas would kind of be that general piece of it. Yeah. But in general, if it has positive and negative, it's kind of the crossover point. Okay. The slope B1, if the value if the x values of 2 points on a line differ by 1, their y values would differ by an amount equal to the slope of the line. So basically, if I take an x of 1, that slope represents the y value that changes for each one. Okay. Two houses differ inside by 150 square feet. By how much should we predict their prices to differ? We go back, remember the slope was the 0.0992. So for an extra 150, since this is a straight line, each step gives us that one extra piece. This is 150 steps, 150 square feet steps. And that gives us a difference of $14.9 thousand. Okay, so before I go over this, I'm going to go back to Excel and I want to go through a couple of different things once we got this. So we showed the slope and the intercept doing the calculation. This was equal to the slope. If I go ahead and open this up, give it a little bit bigger here, and if I click, that's what I entered: slope, the known y's, the known x's, and that kind of give it to us. And then our intercept was just equal intercept, the y's, and the known x's. Once I got that, I built this as an equation. That's the model. The 2.5 times the x plus the y-intercept. We can also do this here. Now I actually added this, so let me go cut this off. So there was our scatter plot again. The trend line is that line of best fit. That would be the trend line, this dashed line in the back. I can also get Excel to build that formula and put it right on the dot plot right here, okay, the scatter plot. So I'm going to go here. I'm going to click on one of these things, and you see it says Format Trend Line. It gives me different things. I can go and kind of match what the shape of that curve is. Is it really curved and exponential type? Is it linear? Yes. Logarithm, it pulls off. A polynomial, if it goes up and down. I can kind of match this thing and do a different type of regression. Okay, but here we're doing a linear. That's what we're only working on here. I'm going to display the r² value. This we're going to talk about in the difference, and then display the equation on the chart. There's those two values. This is not the r that we did. Well, it is related to. This r² tells us basically a different thing than our little r. The big R says how well this model predicts the output. This says it does a pretty good version of it. Okay, the r² could be +1, but this could have been a negative slope. So the r, if I took the square root, I could have had a -1 times -1 is a +1. So this could have been a 1, but have a negative slope. So I have to know to calculate the r, the little r value. I can take the square root. They're kind of related by that way, but I have to add the slope, either positive or negative, to get the real r value, the little r. Again, this is big R. this is basically telling me how well this model fits, not the correlation coefficient. Okay, let's see. So this you can use, there's the 2.5, there's the 2.5, 3.3 gives us the intercept. Okay. So that's what we covered, definitions of outcome or response variables and predictor variables. How to compute the least squared regression line. We went through from R. We learned R times S sub y over S sub x gives us our B1, and then our B0 is just y bar minus their B0 x bar. How to use it to make predictions. We did the models. And then how to interpret predicted values, the y-intercept B0, the slope B1 of the least squared regression lines. The slope, that's the slope. What does that mean? For every individual, we go up or down by the slope. And then the y-intercept is the value at x equal to 0. And that's that was that for the lecture. Okay. So we'll continue on. Next, we have to talk about inferences, basically do some confidence intervals, and then some hypothesis testing of the slope B1 to determine if there really is some value here that is useful. The slope is that useful. Okay, see you next time. Have a good day.